Hello friends, in this short video we are going to see the apparent gain or loss of weight in an elevator which is accelerating or retarding. So what is actually happening? Do we really gain or lose weight? First of all, let us understand four basic terminologies: mass, weight, apparent weight, and apparent mass. So what is mass? Mass is nothing but it is a measure of inertia. It is a resistance of a body against the change of its state of rest or state of motion, which means it is a resistance against acceleration. We know that to establish a flow of current, we need to apply a voltage. All the materials have an inherent resistance against the flow of current, which is given by this ratio voltage upon current, and it is called the electrical resistance. Similarly, to produce an acceleration, we need to apply a force. All the bodies have an inherent resistance to get accelerated, and this resistance is given by the ratio force upon acceleration, and it is called the mass. This is one of the standard definitions of mass. Now, what is weight? Weight is nothing but it is the force with which the earth pulls a body. If there is a body of mass m, then the earth pulls it with a force mg, and this force is nothing but the weight of the body. Since the earth is pulling the ball falls to the ground unless we provide a support. Now you provide a support, you are holding the ball in your hand. The ball is not moving down despite the force mg, which is its weight, is acting on it. Why? Because your hand is providing a reaction force mg in the upward direction. So the net force acting on the ball is zero. The weight of the ball is cancelled by the reaction force your hand exerts on the ball. Since your hand is exerting a force on the ball, then according to Newton's law, the ball exerts an equal and opposite reaction force on your hand. So this force is what you feel as the weight of the body, and it is called the apparent weight. And definitely apparent weight upon g gives the apparent mass. So in this case, as you have already seen, the apparent weight and weight are same. But are they same every time? Imagine yourself standing on the floor. Your weight mg is acting downwards, but you're not moving downwards because the floor is exerting a reaction force mg in the upward direction. So the net force acting on you is zero. Now again, according to Newton's third law, you exert a force on the floor, and this is called your apparent weight, and this apparent weight upon g gives the apparent mass. This is what you feel as your weight or mass. Not only what you feel, but it is also what is measured by this machine. So how does a weighing machine work? The deflection of needle of this machine is directly proportional to the normal force acting on it, and the reading it gives is nothing but the normal force acting on it upon g. Now you just stand on a weighing machine. See, the normal force acting on the weighing machine is not your weight. Your weight, which is shown by the red arrow, is acting on you. The normal force which is acting on the weighing machine is your apparent weight. So the reading it gives will be your apparent mass. So far in our discussions, apparent weight and weight are same. Let us go further to see what happens. Now imagine yourself in a lift which is accelerating upwards. If the lift is accelerating, everything inside the lift, including this man, also will be accelerating upwards. Now, when does the lift accelerate upwards? It happens when the lift begins to move upwards, or when there is an increase in its velocity while moving upwards. It also happens when the lift retards in the downward direction, that is, when the lift is stopping its downward journey, or when there is a decrease in its velocity while moving downwards. So in all these four cases, your acceleration is directed in the upward direction. Now again, your weight is acting downwards, but you're not moving downwards because of the reaction the weighing machine exerts on you, which is equal to mg. So if these two forces are acting on you, the net force on you is zero, and you are expected to be at rest. But you are not at rest, instead, you are moving up with an acceleration a. So a force ma must act on you. But who provides this force? When the motor of the lift runs, the rod that runs over the pulley pulls the lift upwards, which in turn causes the floor of the lift to push the weighing machine also upwards along with it. This causes the weighing machine to push you also upwards. So the force Ma is exerted by the weighing machine on your feet. So the total force exerted by the weighing machine on you is mg, which is the reaction force, plus ma, which is equal to m times g plus a. So according to Newton's third law, you also exert an equal and opposite reaction, which is equal to m times g plus a on the weighing machine. This is what you feel as you weight. So your apparent weight is m times g plus a. This is also the normal force on the weighing machine. So the reading it gives will be your apparent mass, which is equal to m times g plus a upon g. So in this case, it is very evident that your apparent weight is greater than your actual weight mg, and your apparent mass is greater than your actual mass m. So in this case, you have an apparent gain of weight. Now imagine yourself in a lift which is accelerating downwards. So when does the lift accelerate downwards? It happens when the lift begins to move downwards, or when there is an increase in its velocity while moving downwards. It also happens when the lift retards in the upward direction, that is when the lift stops its upward journey, or when there is a decrease in its velocity while moving upwards. In all these four cases, your acceleration is directed downwards. Here also, your weight mg is acting downwards. If the reaction the weighing machine exerts on you is mg, then you will be at rest. But you are not at rest, but moving downwards with an acceleration a. So the entire weight mg is not required to be cancelled by the reaction force exerted by the weighing machine, because the effect of a force ma is visible. So the entire weight mg is not cancelled, but only a part of it, which is mg minus ma, is cancelled by the weighing machine. So the force exerted by the weighing machine on man in the upward direction is mg minus ma, which is m times g minus a. And according to Newton's third law, you also must exert an equal and opposite force mg minus a on the weighing machine, which is your apparent weight. And definitely the reading the weighing machine gives will be your apparent mass, which is mg minus a upon g. So in this case, it is very evident that your apparent weight is less than your actual weight mg, and your apparent mass is less than your actual mass. So in this case, you have an apparent loss of weight. This phenomena can be experienced when you travel in a car also. Imagine yourself in a car over an inclined road. Let A be your acceleration. Then this acceleration will have two components, vertical component and horizontal component. The vertical component is given by A sine theta. Then your apparent weight will be m times g minus a sine theta. So here you have an apparent loss of weight. You also can have apparent gain of weight depending on whether you are moving upwards or downwards with acceleration or retardation. Thanks for watching.